Okay, 4Cs. Some of you were having difficulty yesterday trying to figure out how to get the lengths for the effort distance and the force distance and how the whole torque equations work with this. So let's say we have this set up here. So we got a little lever. Now, this point right here where the stand is, this is going to be our point of rotation. So that's our P. Okay, so the next thing we have to figure out where the load is located. So let's say the load was placed over here, and we'll call it mass load, ML. So the force of this load is located right where its center would be. So it would be acting on the lever right at this point, and because of gravity, the force of the load would be right here. So this would be F. Now, to calculate this, it's just equal to the weight, which is ML times G. So that's the formula to calculate what the force of the load is. Or if you have the force of the load, if you have this already, you can actually calculate that using this formula. Okay, and let's say for the sake of argument, our force was placed like right at that spot there. And it would be, in order for it to balance out, it's got to be pointing down. And this would be our force effort. Okay, so now if we're doing the simplified formula is force effort times distance effort is equal to the force load times the distance of the load. So let's talk about how we measure the effort distance. The effort distance is the distance between where the effort force is applied to where the fulcrum is. Yeah, we'll change that color so it's a little bit clearer. All right, so from this point to the point of rotation. So this here, that length there would be the effort distance. Now the load distance, that one is measured from where the load is located to the point of rotation. So this length right here, this would be the distance for the load. And you'll have to figure out these lengths of both of these based on the measurements I had given you on the diagram. So on the diagram, I actually gave you the full length of the actual bar itself. The dolly actually is what it was. And I gave you some of these distances, but I left some of them out. And you actually had to figure those out by using a little bit of deductive reasoning and some basic addition and subtraction to figure those values out. Okay, so now that's with the simplified formula. But what happens when we have to do the more complex one? Okay, so with the more complex one, and we'll erase this, that's where we actually had to do it from the torque perspective. Now, when doing it from the torque perspective, we also have to include all of the forces. And that means we also had to include the weight of the actual dolly itself. So the weight of the dolly, we treat it as if it's focused right in the middle. So this would be the force of the actual dolly itself. And then at the fulcrum, we actually have the normal force, which is acting up in this direction here. So then when you actually have to measure the distances, instead of using D, we use R, which actually stands for radius, because technically this thing makes a circle. So you have radius E, technically radial length E, but really it's just the distance. So RE, RD, RN, RL, and we have to figure out what all those values are. Well, since the POR is going to be right here at the fulcrum, we know that for FN, it's going to be 0 meters because it's right there on the fulcrum. Now, RE is going to be from wherever FE is all the way to the point of rotation. So that would be your RE amount. RD, same thing, from here to the point of rotation. So that would be your RD. And then your RL is from the point of rotation to where ML is located. So the next thing is when you do the torque equation, the full torque equation, it's going to look like this. So all of these. So when you look at the torque equation, this on the left-hand side refers to the net torque or the overall torque. This first term right here, that term right there is the torque caused by the effort force. This is the torque caused by the actual weight itself of the dolly. And this would be the torque from the normal force. But since it's right on the POR, this actually cancels out. So this vector goes to 0. And then finally, the last term is the torque caused by the load, which is this one right here. So the next thing to consider is, first of all, we're trying to figure out the minimum either effort force or we're trying to figure out the mass so that the system is in balance. Basically, we're assuming that the overall torque is going to be 0 because there's no rotation. Then what we have to figure out is the direction of each torque. So if the force wants to cause the system to turn clockwise, we consider that to be negative. And if it's counterclockwise, positive. So when we take a look at FE here, FE is pulling it down in this direction, which means that this bar wants to rotate this way, which is going to be the counterclockwise direction in this particular case, right? Because it would go in this direction, which is the opposite in which a clock goes. So in fact, both FE and FD would cause the bar to rotate in this direction. That makes these two torques positive. However, FL, but if we take a look at where FL is located, this vector makes it want to rotate this direction, which would be the clockwise direction. And since that is clockwise, that makes this vector negative. And then finally, the formula for torque to substitute in for these is torque is equal to R times. So for example, torque for E is going to be RE times FE. The torque for the weight of the dolly is going to be RD times FD. And then the torque for the load is going to be RL times FL. And then based on the math there, you can solve for the unknown thing that you're looking for. So there are your hints.